find their integrals and how to apply them. So, like examples of these functions are like y equals ln x, and then like y equals e to the x. And without looking on internet or like we don't know what these derivatives are. So we have to bring up an old friend of ours, which is the actual formal definition of the derivative, which is the limit as h approaches 0, f of x plus h minus f of x over h. And this gives you f prime of x. So without like just knowing it through the internet or a derivative calculator, this is how we find the derivative of ln x and e to the x. So let's start with ln x using the formal definition. Alright, so we plug in ln x for f of x, so the limit as h approaches 0, ln x plus h minus ln x all over h. So if you remember from the logarithmic properties, if you have ln a minus ln b, that is the same thing as ln a over b. So we can condense this into a single natural log. So this would be the same as the limit as h approaches 0, and then ln x plus h over h, and then that's still over h. And then I'm going to change it so it reduces with h. What I mean is I'm just going to like cancel out the h's in the natural log, so it'll be something like this. So ln, wait, no, this is x, my bad. I'm going to cancel the x's, that's what I mean. Because it makes no sense for h to come nowhere out of ln x. So this is 1 because x over x is x, and then plus h over x, and then over h. And then I'm going to rearrange it to be the limit as h approaches 0, 1 over h times ln 1 plus h over x. And then another log property is if you have like a variable and a constant in the front, or like any number or variable in front of the natural log. So like say if we have c of ln a, then we can condense into ln a to c. Basically, the coefficient of this natural log is the exponent of the base, if that makes sense. So we can rewrite this as the limit as h approaches 0, and then 1 over plus h plus x, and then this will be ln right here, and then 1 over h. So without doing this with a calculator, this might look really tricky, but there is a special definition. There's a special limit that's similar to this, and it's this one. So basically, as the limit of, like, let's just say it's t goes to infinity, 1 plus 1 over t, and then to the t power, that equals e. So if we can somehow manipulate this function to be similar to this, then we could probably find the derivative of this function. So what I'm going to do is I'm going to put the limit inside the natural log, because this is actually a property that you can use for limits. 1 over h. So what we can do is I'm gonna actually make u equals 1 over t. We're gonna use a u substitution. And since we're going into the u world, we can't have t going to infinity. We have to have u going to a certain value. We have to switch the bounds. We're in the u world now, so we can no longer have any t's. So using this substitution right here, as t approaches infinity, u approaches 0 because 1 over infinity is just 0. So using our substitutions, we get as the limit as u approaches 0, 1 plus u 1 over u is e. And this is actually really similar to the limit we have right here. So using this definition, let's try to make this and this match. So what I'm going to do is I'm going to substitute u to be h over x, and then x times u equals h. But then as h approaches 0, u would also approach 0 because that's just 0 over x, which is 0. So this is just equal to the ln of the limit as u approaches 0, and then 1 plus u, and then h equals x times u, so it'll be 1 over x times u. And then I'm going to have more space. I'm going to add more space. So so equals the ln of 1 plus u, and then the limit inside. Let me make this a little bigger. So equals ln 1, the limit as u approaches 0, and then 1 plus u, and then 1 over x times u. And this is fine because usually we kind of treat x as a different variable, like similar to maybe a constant in this case. So we kind of treat x as a constant, so we can leave it alone. And there's also another exponent property. So basically, if you have e to the a times b, or like not e, so like say if this is like x, let's not get confused with the number e. So that's the same thing as x of a to the raised to the bth power. So if we have our a as u, 1 over u, and then our b as 1 over x, because a times b would be 1 over u times x. So let's make that substitution. So this is equal to ln of the limit as u approaches 0, and then that'll be 1 plus u, and then our a is 1 over u, so 1 over u, and then our b is 1 over x. So we already know that this part is e. So it'll just basically be, we don't need a limit anymore. Sorry about that. We basically solved the problem. It just ln e to the 1 over x. But we have this ln here, so we could, because the exponent is on the top right here, we can bring it down as the coefficient like this. So I'm just basically bringing it over here because that's one of the log properties. And then ln e is just 1 because what ln really is the log base of e. And the log base of e to e is just 1 because e to the 1 is just e. So this will just be equal to ln x. I mean not ln x, 1 over x. So in short, f prime of x is equal to 1 over x, and f of x equals ln x using the formal definition. So let's try to derive the derivative for e to the x. And there's actually, knowing that we know the derivative of ln x is 1 over x, there's actually an easier way to do this without using the whole formal definition. So let's say y equals e to the x. So I'm going to take the ln of both sides. And this is something we're going to use a lot in this unit. So ln e. And I'm just, which is the same thing as ln e to the x. I'm just bringing the exponent down to the coefficient. So this is the same thing as ln y equals x, because this is just 1. So now I'm going to use implicit differentiation. So I'm going to take the derivative with respect to x on both sides. So it's useful that we know that we can actually figure this out because we already know that the derivative of this is 1 over y and then dy dx because it's not being differentiated with x but y. And then this will just be 1 because taking the derivative of this would just be x to 1 and then minus 1 and then times 1. That would be 1 times x to 0, which is 1. So yeah, it's pretty useful that we actually figured out the derivative of ln x, or so we can basically skip the formal definition to find the derivative of e to x using implicit differentiation. So what I'm going to do is I'm going to isolate dy dx, and then you get dy dx equals y. And then if we go back to our original equation, we figure out that dy dx is just e to the x. So it doesn't change at all. And so in short, the two most common functions are like e to the x, so y equals e to the x, and then y equals ln x. And we figured out the derivative, so y prime equals e to the x, and then y prime equals 1 over x. But there are two other functions I'd like to talk about in this video. So there's y equals, like, say, like b to the x, where b is some constant, like b could be 4, b could be 6, b could be any number, as long as it's not dependent on y. It's constant throughout the entire situation. And y equals log b of x. So this might be a little trickier to find the derivatives. So we're basically trying to find y prime for both of these. So I will do that right now. So y equals b to the x. So what I'm going to do is I'm going to take the ln on both sides, bring the, and this is just ln y. Then I bring the coefficient, the exponent down to the coefficient. So this would be ln b. And then I'm going to take the derivative with respect to x. And then it would be 1 over y dy dx. And then it would be ln b. Don't be tempted to put db dx. Even though it is a different variable, it is treated as a constant. So this could easily be ln 4 or ln 3. Just don't put db dx. It'll be a lot more confusing. And so yeah, so 1 over y dy dx, and then ln b. So b is a constant, so treat it like that. Don't take its derivative with respect to x. So let's isolate dy dx, and that'll be y ln b, and then y equals b to the x. So we get that y prime is b to the x ln b. Alright. Now let's try to find the same for logarithmic ones. So we get y equals log bx. So if we were to rewrite this as exponential form, this would be our base, so b, and then basically what the logarithm yields is the exponent of the base. In other words, the exponent would just be y. And then x would be the result of b to the y. So then we can just take the ln on both sides. You're starting to see a pattern. So bring the exponent down to the coefficient. So y ln b equals ln x. And then take the derivative with respect to x. And you get dy dx ln b, and then you get 1 over x. And then we isolate dy dx, and then we get 1 over x ln b.